Hello, my name is Caleb Stoffel, and I'm here with the Trine University Shell Eco Marathon Battery Electric team. We will be competing in Sonoma, California in April, and we are here to present our design for Phase 2. Keep in mind, our car is mostly still in the design phase as we do this for senior design. So we just have primarily theory and CAD models as of now, although we expect to have a full prototype by the end of January. Feel free to pause this video at any time to look at the photos or diagrams for extended periods. We want to be thorough with this presentation, but we want to also keep it brief. Here's a list of our team members, including our advisor, our driver, and our reserve driver. Here's an outline of our presentation, so you have an idea if you want to skip through to future sections. We had a team compete in the Shell Eco Marathon in Detroit in 2017. They passed technical and safety inspections. They achieved 42 miles per kilowatt hour, which gave them a placement of 15th overall. Some major problems we identified from the previous year were that they had a monocoque design, which led to misalignment due to flexing of the shell. This led to brake rub, taking away much of the energy of the car, and it was overall very heavy. We had problems with steering, including missing a degree of freedom. We did not meet the Ackerman condition, and there was scrubbing in our steering. We also had a brushed motor, which was rather inefficient, and we had other problems with our electrical, including having a solenoid, which was inefficient. So some major things that we want to improve from last year: we want to add an aluminum frame, which will eliminate misalignments and hopefully eliminate brake rub. So our shell ideally will become protective only. We want to change from carbon fiber to polycarbonate shell so that it can be thinner and lighter weight while remaining rigid and protective. Our steering, we definitely want to add the Ackerman condition, and we want to have a brushless hub motor. This will simplify our drivetrain, and a brushless motor will be much more efficient than last year's. And we want to replace our solenoid with a solid state relay. So again, these are some of the major improvements we are looking to do from last year's team. Here are some of the safety design requirements that we've already met, and the dimensional requirements that our CAD model already meets. Let's get into some of the CAD. I'm going to start basically breaking down our car layer by layer so you can see all of the features of the car thus far. Here you can see the car most completed. It has its rather clear polycarbonate shell with a bubble on top. This will be clearance for the driver's head and will give the driver greater visibility, while the roll bar is still around 75 millimeters above the driver's head. Here's the car without any shell around it. This car, we realized, does not have fenders around the wheels. We plan to add those, we just did not have them yet. But the driver does need to be isolated from the wheels with fenders or coverings protecting the driver from the wheels and brakes. Now I'm going to start zooming into different subsystems of the vehicle. The area circled in red will be enlarged to see in greater detail. Here you can see the turning knuckle interface with the brake, the rotor, and some of the steering linkages. Here is the hub motor interface with the rear wheel and the rear part of the frame. Here you can see the roll bar interface with the frame. Here is a universal joint we decided to add to our steering column. This will allow the driver to move the steering column out of the way quickly when the driver needs to exit the vehicle within 10 seconds, and also just for safety. Here's a driver's view of the steering mechanisms. This will give a good idea of how our steering linkages connect. Here are illustrated 5 anchoring points for the seat belt and safety harness.
Hi, my name is Ben Miller, and I've primarily been in charge of doing research and design for the frame. So I'm just going to go over a few of the key points and what we hope to accomplish with the frame this year. So just an overview, we think that if we add a frame instead of using the monocoque to support the weight of the car, we'll be able to remove some misalignments. Also, we can add structural support for the driver and the roll bar, and we also want to reduce excess weight caused by the monocoque. So if we use a frame and we make that light enough, we can decrease the weight of the shell and overall decrease the weight of the car. For the frame, we're using 2 types of aluminum, 6063 and 6061. The 6063 is used in places where we have to do bending, and the 6061 is used everywhere else. In order to fabricate the joints for our frame, we'll be using Scotch-Weld DP420, which is a 2-part epoxy. What this epoxy does for us is gets rid of the need for our team members to TIG weld. The epoxy itself is rated for 4,500 psi, but when doing some tests in-house, we found that we were able to get it to hold 2,300 psi. So based on those results, we're using an average contact area per joint of 8 square inches, which is going to give us well over the amount of strength that we're going to need for each joint.
Hello, my name is Jordan Lolito, and I'll be talking about the shell. As you see here, this is the visibility bubble. This is what the driver will be seeing out of. The back portion is elongated to allow for a more streamlining effect. Because of this, we had to add a bulkhead to keep the driver's head separate from the electronics compartment. Going deeper into the shell, we'll be talking about the top and the bottom. The top and the bottom will be made out of polycarbonate. The top will be a 32nd inch thick. The bottom will be an 1/8 inch thick. The estimated weight reduction from a carbon fiber shell will be 9.5 kilograms. The polycarbonate will maintain its rigidity and safety of the driver as compared to the carbon fiber shell.
Hello, I'm Zach Rowland, and I'm in charge of the steering on our car. For the steering on our car, we plan to use a 4-bar linkage which will connect our left turning knuckle to our right turning knuckle. Also on our left turning knuckle, we will have another rod that is connected to our steering column. The steering column will have a pitman arm attached to it, which when turned will turn the left steering knuckle and right wheel. Lastly, on our car, we plan to utilize the Ackerman geometry in order to reduce the scrubbing, which caused issues from last year.
Hi, my name is Jordan Lolito, and I'll be talking about the brakes. The group has heard of the infamous brake test, in which the front and back brake systems must be activated independently of each other, while the car sits on a 20% grade. The group will use hydraulic disc brakes for both the front and backs and will create a custom splitter for the front brakes. The brakes will work in conjunction with a 160mm rotor.
Hi, my name is Chris Ferguson, and I will be in charge of the hub motor, which will be our propulsion system for this vehicle. So here you can see a picture of the hub motor that we have selected. However, we are waiting on the track profile to properly select the motor that we are going to use. However, we have a rough idea of the voltage rating, power rating, and what kind of torque that we're going to need. So here it's a brushless DC hub motor. It will support a 160mm rotor for our brakes. It's 36 volts, 750 watt input power, and its peak efficiency is roughly 87%, where its max torque is 42 Newton meters.
This is Spencer Fall, here to talk about our motor controller and the electrical schematic for our vehicle. This year we're planning on integrating a brushless hub motor compared to the brushed chain drive system that was used in last year's car. We're designing our own motor controller, and we're currently on our second iteration. We're attempting to develop two designs concurrently. One comes from designs that were given to us by Duke University, but we haven't gotten as far on those designs yet. The ones you're about to see in the schematics are based on a Stanford motor control lab. It utilizes the DRV8332 motor driver to create the proper signals to run a three-phase BLDC motor. Now for the electrical system. The first schematic is the overall electrical schematic for our vehicle. As you can see, we're getting power from a 48-volt battery. That power is flowing through a line that has a 20-amp fuse and the emergency stop switch in it. The horn circuit comes before the joule meter, as we don't have to measure the amount of energy going through the horn circuit. This all leads up to the driver kill switch, which is attached to the activation side of the solid-state relay. On the power side of the relay, we have the motor control circuit, which contains the motor and this black box controller, which you're about to see in more detail. This schematic is an overview of the controller circuit. I'll show all of these in more detail as we go. The power converter board uses two buck converter circuits to provide 12 volts and 5 volts from the battery voltage of 48 volts. These power converter circuits basically come straight from the data sheet of this buck converter chip. The 12 volt source then goes out to the driver board, and the 5 volt source powers our microcontroller. This schematic shows our driver board. The DRV8332 chip contains FET-H bridges, which are internal to the chip. It receives PWMs and reset signals from the microcontroller and uses these signals to output proper signals to the motor that are at the battery voltage. The inputs and outputs to this board go through isolated screw terminals. And this final schematic shows which signals are traveling to and from our TNC 3.2 microcontroller. The TNC receives position data from the motor's Hall effect sensors and uses that data to send the correct PWMs and resets for commutation. It also receives fault signals from the driver board, and it uses an internal ADC to read the throttle potentiometer, which adjusts the output duty cycle.
This is Caleb again, covering the battery/battery management system. This year we will be using a 48 volt lithium ion battery. It'll be a 10 amp hour battery with a built-in battery management system that will allow a maximum of 50 amps. And this will be purchased from Electric Rider. We stuck with the same vendor as last year, where we used a 36 volt battery, but this year we decided to go with the 48 volt. But we were attracted to this battery because it has the built-in battery management system. Our team was also able to roughly predict our performance for this year. We put our last year's car in a custom dynamometer. We analyzed the losses from the drivetrain, wheels, motors, electrical, etc. And then we modified the losses that we found there to model that of an ideal's design for this year. Assuming projected improvements, we lessened some of the losses. A lot of them went near to zero, especially things like brake rub, because we expect to eliminate that completely. Then we also imported data from a brushless hub motor manufacturer, and we found that we can achieve 300 miles per kilowatt hour. Now we know that this analysis will have some shortcomings. This does not account for all energy loss. Misalignments, scrubbing, things we cannot necessarily control down to a zero loss level are not accounted for in this analysis. We're also relying on data from third-party sources, and this analysis is based on a track from Detroit 2017, so it will be different for this year. So to conclude this video, we understand the safety and technical requirements for the competition. We will definitely be making some significant improvements from our performance last year. We should have a physical car by the end of January for then testing and to improve for any unforeseen issues that we may have. And our analysis shows that we should achieve around 300 miles per kilowatt hour, although we know that this is more than the first place team from last year. We predict that it will be lower than this because of shortcomings in our analysis and energy loss that we cannot model. Thank you for your time. We look forward to seeing you in California, and have a great day.